So now we come to my favorite part where we synthesize everything we know about first derivatives, second derivatives, increasing, decreasing, concavity, determining those points of inflection, max and min values, as well as any points on the curve. Okay? So we have this procedure for graphing, and we do all of these things, maybe not necessarily in this order, but we need to be able to determine all of these values. And some of it we use algebra, and then a good portion of it we're going to be using calculus. One of the first things we'll always do is we'll look at a function and determine its domain, and that's algebra. We've been doing that for a while. We can also determine symmetries if the function is odd or even. And so we know that f of negative x equaling f of x, that's the definition of an even function, and f of negative x equaling negative f of x is an odd function. You should have learned that in your algebra class before this. Okay, so determine any symmetries. I don't always do that, but it's helpful. We're going to find that first and second derivative. We're going to find critical points. Critical points occur when f prime of x is equal to 0. We're going to determine where the curve is increasing or decreasing. So we're going to test in the first derivative when we're doing that. We're going to find points of inflection. That's going to come from setting your second derivative equal to 0. And then determining concavity, that would be if f prime of x is positive or negative. Any asymptotes, if it's rational, we could have horizontal asymptotes or vertical asymptotes. Logarithmic graphs have asymptotes. Exponential graphs have asymptotes. Some of our trig functions have asymptotes. Well, all of them except for sine and cosine. And then we'll plot key points. So we can make a table of values, plug in an x, get out a y as we need. So let's sketch the graph of this function. The first thing we would do would be to identify the domain. And because this is a polynomial, it's a quartic polynomial, for my domain, I know that x is from negative to positive infinity. There are no symmetries here, not as important, but f of negative x equals negative x to the fourth minus 4 times negative x cubed plus 10 would simplify to x to the fourth plus 4x cubed plus 10. And either all of the signs change and that makes it odd, or none of the signs change and that would make it even. And what you see here is that we had only one sign change from that original function. Just this negative became positive. So I'm going to run through this. I'm going to find my first derivative. F prime of x is 4x cubed minus 12x squared. And because we always want our functions written in factored form, this is the same, my first derivative, as being 4x squared if I factor out that GCF and x minus 3. So my critical numbers are going to be x equals 0 and positive 3. All right, my second derivative, f double prime of x, that's the derivative of my first derivative, I end up with 12x squared minus 24x. And again, I want to factor it because it's going to make my life easier later down the road when I have to plug in numbers to test. It's easier to test in the factored form. So I'll factor out a GCF of 12x, and that leaves me with x minus 2. So my inflection values are either going to be at x equals 0 or positive 2. So these are our two values. And in order for us to determine increasing and decreasing, we can do this separately and make two separate tables, which I know your homework that you work on will have you do it separately. But what I prefer to do is to make it all on one table. All right, so we have our function f of x equals x to the fourth minus 4x cubed plus 10. And we're dealing with some numbers on this. I'm going to just space those out a little better. We have 0, 2, and 3. So 0, 2, and 3, these are x values. All right. And we're going to need to choose a test value on each interval. So my test values, I can choose any number I want. X equals -1, x equals +1. Between 2 and 3, I have to pick a non-integer value. So 2.5, and then x equals 4. And we want to test these in the first derivative because the positives and the negatives are going to let me know increasing and decreasing. And then we're going to test them in the second derivative because the positives and negatives are going to let us know about concavity. So my first derivative, f prime of x, is 4x squared x minus 3. So I need to determine what I get for f prime of -1, f prime of +1, f prime of 2.5, and f prime of 4. And so this is where I say, the factored form makes our life a little bit easier. Because whatever I plug in here, this first term is always going to be positive, right? So I'm going to have a positive times whatever sign I get there. And it's really easy for me to see, well, if I plug -1 in, -1 minus 3, that's a negative value. So I have positive times negative, and positive times a negative is negative. So I know I have a negative value here. All right? So running through this, and you should check this on your own, f prime of 1, I get a negative value. F prime of 2.5, I get a negative value. It's not till I get to f prime of 4 that it becomes positive. So I know we're going down, 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 decreasing, 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 and then we turn around and go up, increasing. So what we can say is the graph is decreasing when x is from -infinity until we reach 3. And it's increasing from 3 to +infinity. So we're going to use that part of that information. And then we have one other thing to talk about, because when we change from increasing to decreasing, up to down, there's a max, or down to up, decreasing to increasing, there would be a min. And so because there's a change in sign, we're going from positive to negative, or negative to positive right here. When we change signs, that lets me know I'm going to have a min. So I can say there's a min at x equals 3. All right, so we've been able to make some conclusions, but I'm going to need to use my second derivative as well. So f double prime of x is 12x times x minus 2. And so again, I run through this process. F prime of -1, f double prime f double prime of positive 1, f double prime of 2.5, and f double prime of 4. And so I want you to see I've listed this. I've kind of made us some columns here. And you don't have to do it this way. You can do it separately. It's just, for me, it's an easy way to keep things organized. So again, I'm going to run through and test each one of these numbers in my second derivative. So for negative 1, I would say 12 times negative 1, that's going to be negative. Negative 1 minus 2 is negative, and a negative times a negative, of course, gives me a positive value here. So plugging those numbers in, I get positive, negative, positive, positive. Positive lets me know I have concave up. Negative lets me know I have concave down. So I've got concave up, concave down, concave up, concave up. And before we start doing, okay, concave up like a cup and concave down like a frown, we want to remember that concavity has an increasing and a decreasing portion with each of them. So we have concave down increasing, concave down decreasing, right? So it went up and then it went down. Similarly, we've got concave up decreasing and concave up increasing. So when I draw my curved section, I'm only going to draw the left or right side of these frowns or smiley faces, considering what I have written up in red for the increasing and decreasing intervals. So concave up decreasing looks like that. Concave down decreasing, concave up decreasing, and then concave up increasing. And wherever my concavity changes sign, that is an inflection value. So when we change from positive to negative or negative to positive, at x equals 0 and x equals 2, we've got inflection at x equals 0 and inflection at x equals 2. And if I were to write my intervals for concavity, we would say that we are concave up when x is from negative infinity to 0, union 2 to infinity, and concave down where x is from 0 to 2. All right? So, and then my inflection points and my max and min, I would get all of those values. Those are ordered pairs. So I've got inflection, 0, some y value, and 2, some y value. And then I have that there's a minimum at x equals 3. But remember, the minimum is y at the x value. So there's a minimum at 3, some y value. And if I want to determine what those y values are, I need to make sure that I go back up to my original function. And my original function is f of x equals x to the 4th minus 4x cubed plus 10. So if I plug 0 and 2 and 3 in, I'm going to get these output values that I can plot on my graph. If I plug in 0, I get out 10. If I plug in 2, I get negative 6. And if I plug in 3, I get negative 17. So let's graph our curve. So I've moved over to some fresh space here. And we have points that we're going to plot. We have a point at 0, 10. I'm going to count by 2, so 2, 4, 6, 10. And just because it's going to make my graph look nicer. And I have a point at 2, negative 6. So over 2 down negative 6, roughly here. And then also 3 down negative 17. And I'll just put that down about here. My y-axis doesn't have to be perfectly to scale. So I have 2, negative 6, and 3, negative 17. So we're going to think about graphing this because we were dealing with a quartic polynomial with a positive leading coefficient. We know my end behavior. Both ends are going up. So we know we're going to start high and we're going to end high. Okay? Back from algebra logic there. So we're going to start high, drawing left to right. So going back and looking at your table, the graph was decreasing from negative infinity to 0. So it was going down. And it was concave up. So drawing this, I'm going to draw more or less the left part of a smiley face, decreasing, concave up. And then from 0 to 2, the graph was still decreasing. We're still going down, but that concavity changed. So we're going to draw the right half of a smiley face. That doesn't look very nice. So I'm just going to kind of go like this, nice smooth concave down. All right, between 2 and 3, still decreasing, but now my graph is concave up again. So, you know what? I'm just going to move that point, make it look a little nicer. And then at 3 to positive infinity, the graph starts moving up. So far we've been decreasing and we've had 2 changes in concavity. And now the concavity stays the same. We're still concave up. But we're increasing forever. So we've graphed our curve. The x-intercepts for this function, this is the function we were graphing, f of x equals x to the 4th minus 4x cubed plus 10. That's difficult for us to factor and find the x-intercepts. So, I mean, we can do it and find what these 2 values are where we're crossing exactly, but that's not what we need to do. That's an algebra problem, and we're focused on the calculus here.